All right, let's talk about this page, this next page. I want to think about something called X and Y components. So fellas, I'm going to draw you back in again. This next page, we're talking about X and Y components. And some people talk about it as decomposing a vector. I guess that makes sense because decomposing in like biology is when things rot and break down, I guess. But when we're decomposing a vector, when we're finding its components, we might think about having a vector, I don't know, that goes off at an angle. And somebody might say, okay, well, this vector goes off at an angle. If I had decomposed this into X and Y components, what I would be talking about is finding the X portion of that vector and the Y portion of that vector. And so I might talk about having a force, and I could even call it F1, force 1. Force. This could be like a force. Force 1. And I might talk about there being like an X component to a force. I would call that F1X. And I could even have a Y component to a force. I could call it F1Y. Those would be the components. And there could even be an angle that force 1 went off at. I could call it theta. And you can imagine that if I knew force 1 and I knew theta, I could use SOHCAHTOA to get F1x and F1y. Right? I could just get those vector lengths, just like sides of a triangle. Or I could come at it at another angle. I could say, hey, if somebody told you that F1x was equal to 10.0, now maybe you don't know this yet. Anybody know what the unit for force is in SI unit? It is. It's newtons. Newtons. Just like Isaac Newton. It's his last name. If F1x was 10.0 newtons to the east, and F1y was 5.0 newtons north, somebody might say, could you please find the components? Somebody's decomposed this force into X and Y components. I would like to take these components and find the resultant. Could you please find the resultant force? And if I was going to do that, I'd say, okay, well, no problem. The resultant force, F1, is equal to F1x squared plus F1y squared, all square rooted. Because really, this is just Pythagorean theorem. If you're not quite sure how I jumped to that, what we're saying is F1 squared is equal to F1x squared plus F1y squared, and then just square rooting both sides. Okay? Now, this is just like the stuff we saw when we were in grade school. It's just that it's not ABCs anymore, right? We're using like meaningful subscripts. We're using variables that matter. ABCs was baby talk. This is when we were figuring out the vocabulary and the grammar of math. Now we're going to use it. We're going to apply it, like conversationally, like to something useful. All right, so we've got some forces, and we can sub in our values. We can say, okay, 10.0 newtons squared plus 5.0 newtons squared, all rooted. Somebody with a calculator who's quick on the draw? Yeah. 3.872. Sorry, say that again? 3.872? I don't think so. That would be smaller than either of them. I got an 11.18 on the table. Yeah? There might be some data entries on that one that got to be fixed. It should be about 11.18, and I get 11.18033 dangling off the end. All right. In terms of direction, we still have to get that theta because it's a vector. So again, I still think that tan theta is the strongest ratio here because somebody got 3 point something. That could be a data entry. And even if you did a data entry, and got the hypotenuse incorrect, these guys haven't been affected yet. So we can still get the direction right, even if we made a mistake on the hypotenuse. So we can say, okay, well, the opposite here is the F1y. Looking at my picture, the adjacent is F1x. Remember, adjacent is just a fancy word for beside. Opposite is a little more common in everyday English, easier to remember maybe. Theta equals tan inverse. I could rewrite my formula as I should, I suppose. F1y over F1x. Sub in my values, theta is equal to tan inverse of, what was it? Y was 5 newtons divided by 10 newtons. Pop this up to the top. Make sure you're not in radians. What's the angle going to be? I want to hear from somebody I haven't heard from in a minute. What is it? 26.565. Nice. 26.565. I'll say 5.1. Yeah? Degrees? All right. And so we could say, like, here, I've kind of blocked myself into a corner here, I suppose. But I could say that F1 is, looks like we only have 2 sig figs. 11 newtons. And you know, I didn't give myself a reference frame here. Let's choose the reference frame from the previous page. North, south, east, west, positive, positive, negative, negative. So it would be, based on my diagram, east 20, oh, it's going to round up to 27. 27 degrees north. Yeah, it rounds up because it's just beyond the 5. Yeah. And of course, yeah, you could say, but hardly anybody would say north 63 degrees east. Those would be equivalent statements, but most people would just say the top version because it's the more acute anyway. But then it gets more complicated because we got a single angled vector here that we could turn into x and y components, or maybe we start off with x and y components and turn into the hypotenuse, one way or the other. But then there are other times when you have a bunch of vectors that are at weird wonky angles. So I got 3 vectors being added up. I want to add these vectors up: displacement A, displacement B, and displacement C. And if I wanted to claim that I wanted to add these up, this is my visual way of saying what I just said out loud. But if I wanted to draw them tip to tail, it would look like this. And people are like, well, how do you do that? Because as soon as I look at that, this doesn't look like, you know, in math class we do a lot of sine law and cosine law and things like that. And I don't have like a quick way to turn this into some sort of a polygon or something that I know from math class. And so we have to have a new tool set. The new tool set has to do with this idea of components that I was mentioning up above. We need to be able to take a vector like displacement A and break it up into x and y components. That vector B, break it up into x and y components. So I want to put some information on here. I'm going to zoom in to make it easier to see, and I'll reset my focus. I want to say that I've got a displacement A that's going to be, I'll make it nice round numbers, 10.0 meters. So nothing intimidating with the units, nice and round. And I'll make this be 30 degrees, 30.0 degrees relative to the horizontal. This one here, it's going to have its angle. It's going to be at 40.0 degrees. And this guy is going to have a magnitude of 10.0 meters. So again, 10 and 10. And then the last one's going to go straight, I'm actually going to use north, south, east, west, but it's going to go straight towards the east at 10.0 meters. And we can set our reference frame. We can use the same reference frame as before. Again, I'm just using the same reference frame over and over again to keep things simple and consistent for the note. But I can't just add those guys up. The answer is clearly not 30. We can all see it's 30. Everyone knows it's not 30. Just like you can't just add up sides and expect it to be equal to the hypotenuse, right? This is not going to be 30. we're going to have to do something else. And so the something else that we're going to need to do, and I'll be color-coded about this, okay? We're going to need to take this angled vector and treat it like the hypotenuse of a triangle. And I'd like to find its vertical component. And I'd like to find, oh, I said I was going to be color-coded about this. I'd like to find its horizontal component. And I would give those things a name. If the hypotenuse is delta dA, I'm going to call this one delta dA y. This other one would be delta d a x, the x component. And you know what? I would do the same thing for the next one over. I would say, hey, I should be able to use my SOHCAHTOA to take that hypotenuse with that angle and recognize that x and y are always, by definition, at right angles to each other. So this is a right angle triangle scenario because the definition of x and y is perpendicular to each other. And I should be able to make myself, through SOHCAHTOA, an x component and a y component. And of course I would have a delta d b y and a delta, oops, I said I would do colors, delta d b x. But then I breathe a sigh of relief when I get to vector c, because isn't it all just x, right? Like, whew, don't have to do any trig on this one. This one's just 10.0 meters. And people say, well, okay, that's all well and good. Let's just do that first, okay? Then we'll figure out what we're going to do with all that information. And that's what I got down below here. So I'm going to zoom out just a little bit. What I want to propose is this thing down below is me shifting my mindset to saying, yeah, I know that I'm going to add up these vectors tip to tail, but now that I've thought about x's and y's, I actually am going to shift my brain to think more like a spreadsheet. And what I want to propose is that in math class, we're always very committed to sine law and cosine law and all that sort of stuff. But if I can break this all up and turn it into a spreadsheet, then I can think about column and row kind of addition of stuff. And it's a nice bookkeeping way of doing things. Also, if you're somebody who's into coding and into working with spreadsheets to automate what you're doing, this way of thinking is a great way that dovetails with working with software. So in math class, we have like these free-floating triangles, right? And it's kind of hard to software that. It's hard to turn that into like a math algorithm that fits with programming. I want to propose that what we're about to do right now, even though I know that this isn't a programming class, a lot of you people are going to be engineers and whatever, and it makes sense that we should be able to be building a foundation that connects with that model of thinking, okay? So for the vector A, I want to think about the x information first. So I'll just put a little x here. I'll put a circle around it. I want to think about vector A, and displacement A in the x direction would be equal to displacement A, that's the hypotenuse, times cosine of theta A. Theta A is 30 degrees. Where did that formula come from? Well, think about it. If the delta dA went over to the other side, wouldn't this just be adjacent over hypotenuse? So I've just taken the adjacent over hypotenuse equals cosine theta and rearranged it a little bit. That's all it is. And if you want to write the adjacent over hypotenuse equals cosine theta and then write this line, you can do that, okay, if that makes more sense to you. But I sub in my values. I say displacement A is 10 meters. I say cosine of theta A is 30 degrees. I can come up with a nice round number. Somebody with a calculator, help me out. What's the nice round number? Actually, give it to me like 5 decimal places. What's this nice round number to 5 decimal places? Starts with an 8, if that gives you some feeling of confirmation. Yeah? 8.6602. 8.6602. Is there a 5 at the end? Yeah. Beauty. All right. I never trust my own notes, you know. All right. I want to switch colors. I'm going to switch to red. And you know what? I think I really am going to embrace this spreadsheet right now. I put myself a horizontal construction line there. And I'm going to switch to red, and I'm going to say delta dA in the y direction would be delta dA, the hypotenuse, times sine of theta. Again, this is just the sine ratio. Let's say theta A. I sub in my values, 10.0 meters times sine of 30. This one must be nicer. Isn't sine of 30 one of those magic angles? You guys remember what's special about sine 30? What's it equal to? You guys learned that in grade 10?
What? Sine 30 is a half.
It's a half. Sine 30 is a half. People call it a special angle. Magic triangles. But sine of 30 is 0.5. 0.5 times 10 is going to be 5. So 5. We'll take it to 3 sig figs, but 5.0 meters. All right, let's do the same thing for B. Delta D Bx is going to be equal to delta D B times, I got to be careful here. I almost said cosine of B because I was just following patterns. My brain really wants to be a pattern thinker. Can you guys see that in this case, delta dB is the opposite of the 40 because of where the 40's been measured? So that means that I'm going to use the sine. So I can't just say, whenever I find x components, I'll use cos. Whenever I find y's, I'll use sine, or some silly thing like that. I got to actually look at the triangle. So I'm going to use sine of theta b because I'm finding the opposite this time, not the adjacent. And if you're not familiar with your SOHCAHTOA, I actually did put an extra SOHCAHTOA grade 10 math worksheet into your homework package. You should go back and make sure you can do that, okay? Because you need to. You need to be able to do that. If you haven't gone back and found that, I can show you where it is later. Solutions are posted, okay? You can definitely do that. All right, so we sub in our values. It was, all these guys have a magnitude of 10, so that's easy. Times sine of 40. And again, nice round value to 5 decimal places. What do we get? Yes, sir.
6.4378.
So 5 decimal places. Give me another one.
7.
7. All right. Nice round value. Displacement B in the y direction is going to be delta dB times cosine of theta b. Sub in my values. Again, now this one actually is not round at all. I'll finally admit it. Somebody to 5 decimal places. What's delta dBy? Hey, you know what? I'm just using subscripts meaningfully, consistently. They're always smaller. They're truly subscripts. My D's are all lowercase, and I'm being consistent about how I'm using my subscripts, okay? Be careful about your notation. People want to be able to follow it. Anyway, what's delta dBy? Somebody who's got it. Yeah?
7.66044.
Nice. Meters. And as I finally get to C, I think to myself, this is easy. Delta D, I could write it like this. Delta D Cx is just equal to 10.0 meters. And delta D Cy, if you even wanted to bother writing it, is 0 meters because it's completely east, right? That was easy. But again, I'm going to throw myself up another spreadsheet style construction line. And I want to think about how I'm going to handle this. Let's go back up to this diagram. It seems to me that delta dA goes up by this y amount, and delta dB goes down by this y amount. Agreed? And so it seems to me that if I add up these guys, I should be able to figure out what the difference is. You see what I mean? And the difference is how much I actually ended up going south by. Really and truly also, isn't delta dBy negative value? I should slip in a directional negative sign there because I recognize what's happening with the reference frame. This guy's going south. The other thing, in the x direction. Delta dAx goes over like this. Delta dBx goes over like this. And so think about it. Shouldn't I just be adding up this guy plus this guy plus this guy to talk about how far I've gone over to the east? Just adding them up. So I want to think about that. This is not a perfect spreadsheet. In fact, if it was going to be a perfect spreadsheet, I would carry over to the right here. My page isn't wide enough. I would say I'm going to add up all this x stuff. I'm going to add up all this y stuff. And if I had an extra column over here, I would do it over there. But I'm going to do it down here. What I want to say is delta d x total is delta d ax plus delta d bx plus delta d cx. And I've got x information right up here. I've got y information here. I could add this up. I could say, okay, well that's my, and again, for lack of space, 8.66025 meters plus 6.42787 meters plus, looks like 10.0 meters, and I end up getting 25.008812 meters. Beauty. In the y direction, delta d y total is going to be delta d a y plus delta d b y plus, well, 0, because delta d cy contributes nothing. And I sub in my values of 6.427. Oh, that wasn't the right one, was it? It was 5. Took from the wrong spot in my spreadsheet. 5.00 meters minus 7.66044 meters. And I get negative 2.66044 meters. And people say, well, what are you going to do with that information? Well, it seems to me that I've gone over 25 meters and gone down about 2.66 meters. Or I've gone east 25 meters and gone south about 2.66 meters. If I was going to draw that out, that means that I've gone east, in total, I've gone east that amount, and I've gone south that amount. This is my vector diagram, tip to tail, clearly not to scale. I'm just trying to say that this one's smaller than this one. It should be a lot smaller, in fact, like a tenth the size. But once I do that, I think, I should just be able to take those two components, and doesn't this feel kind of interestingly, look at this picture here, and look at the picture at the very top of the page. Isn't this the same level of difficulty now? Now we've like reset what used to be a really complicated question. We've thought like spreadsheet people, we've decomposed it, and we've turned it into a question that a grade 10 kid should be able to do, no problem, right? Like this is just a right angle triangle where we're going to take these two values that we know, delta d y total and delta d x total, and what we're going to do is we're going to find out what delta d total is and the angle at which it goes off at using SOHCAHTOA, using Pythagorean theorem. We should be able to do this, no problem. And so what I'm going to do is I'm going to put the answers up on the screen, and you can take a screenshot of it, you can take a photo of it, but I'm going to challenge you to just make sure that you can take this to completion, okay? So I'm going to put the answers in my old handwriting from a previous day up on the screen there. You can take a screenshot or whatever, but I want you to just make sure that you can get to this point on your own, okay? Okay? And just to be clear, we're just putting some like beginner level grade 10 SOHCAHTOA and Pythagorean theorem stuff into a physics context. And we are knocking it up a notch by having to deal with these spreadsheety type ways of thinking.